Okay, so let's start with this. I need the derivative with respect to x of sine of this tau, right? What's the derivative of sine of a tau? Cosine of the tau, right? And the tau is everything that was in there, yes? Don't change it, just put whatever was in here. That's the beginning, right? We've taken care of the sine. Times. Now chain rule says now go inside and take the derivative of what was in here. So I need to take derivative of what was in here, right? Man, okay, that's going to be a mess. I have two separate terms, don't I? I have subtraction, so I can do those separately, can't I?
You have to take care of the product rule first.
And I have to take care of the product rule. But I can treat them separately. Like I can go find the derivative of that, right? And then I can find the derivative of that and then just put a minus between them. I'm debating, do I try and do this all at one time?
Yes.
Let me try and do it all at one time and see if you can keep up with this or not, all right? The class average was an 80 on that test, so let's see. All right, so I'm going to put a big set of parentheses here, okay? Because everything I get from here on out needs to be multiplied times this. All right, let me focus on this first. Product. So you've got to do derivative of the first one times the second plus the derivative of the second one times the first, right? What's derivative of x to the fourth? 4x cubed times dx dx, right? Which means you're going to have a 1, so it's just 4x cubed. Yeah? 4x cubed times what? Y. Okay, that's the derivative of the first one times the second one. Product rule. Plus, now the derivative of the second one. What's the derivative of y with respect to x? dy dx. Not 1, right? dy dx. Times, so that was a derivative of the second one, right? Now times the first one, x to the fourth. That's what the product rule looks like. Now, let's finish it. Okay, let's finish it, then I'm going to come over here and do something. Minus, now I need the derivative, I did minus right here, now the derivative of this, which is, with respect to x, 3y squared times dy dx. Okay. Yeah? I'm just going to show it over here. When I took that derivative over here, when I did that product rule, right, and got this, what I did was this. I said I need to take the derivative with respect to x of the first one times the second one plus the derivative with respect to x of the second one times the first one. And then this required the chain rule, 4x cubed times, now the derivative of x with respect to x times y, plus, now this doesn't turn into 1, it's just dy dx, and then times x to the fourth. That turns into a 1, and that's where this comes from. All right, but I did that all like in my mind as I was moving from left to right. Yes? Implicit differentiation. I don't know, should I tell you the story now? I'll tell you the story now. Okay, I usually tell all my Cal 1 students this story. So, when I was in graduate school studying math, grad school really kind of, it becomes all you do. Like it was all I did was math. I was teaching at the university as I was a graduate student, so I was either teaching or studying or in class, and so I lived at the school. I mean, I'd literally, sometimes I'd go like 4 days before I'd go home. I'd sleep on a bench in my office. It was just, all I did was math, right? So that's not healthy, okay? So like once a month I would just go out, right? And we didn't have Uber back then, so I'd just catch a cab. I'd go to this club, this one club, right? It's called The Level, right? And it was over off Fredericksburg, I think. Actually, I went to the place the other day. It's now a restaurant. I went in there, and they still have I was like, I went back in time, I had these flashes. Anyway, So I used to go to this club and get dropped off by a cab, Shiner Bock and Goldschlager shots all night long, dancing, going crazy, right? So I had this rule, right? And this is going to sound real stupid and arrogant and dumb, but just hear me out. Because all I did was math, that's all I had to offer anybody. Whenever I met a girl or something, and I never went up to girls because I didn't have time for them. So like, if a girl approached me, right, then my first question to them was, what's the derivative of x? Okay? It was just like my minimum bar question, because like, you've got to at least know the derivative of x, right? Like, or else we're not going to have any conversations, because this is all I do is math, right? I know it sounds stupid, right? But that's just the way I was thinking. I was dumb. Haven't changed much, but I'm admitting it's dumb, right? So this one night I'm there, I'm on the dance floor, and this kind of always seemed to be back in front of this girl dancing together. And I wind up going to the bar. She comes up to me. I ask her, what's the derivative of x? So what do you think her answer was? 1 is what I expected, right?
0.
She answered with respect to what? And I was just like, oh, yes, yes, okay? Because she understands this. She understands that when you say derivative of x, we all normally would say 1 because we're assuming it's with respect to x, right? But really, we have to be clear on what we're differentiating with respect to, or else it's not 1. So she asked, she answered like with respect to what variable, and I was like, wow, okay. So then I asked her. I never had a second question in mind, okay? But I was like, okay, so I'm going to see how far I can go with this. So my next question, I told her, and I'm going to say it the way I said it, and then I'll explain the question. And we may have talked about this. Talked about all the numbers between 0 and 1, right? And picking a number out of there, right? So I asked her that question, but I asked her mathematically. So I said, what's the probability of picking a rational number out of the interval 0, 1, is what I asked her. And she said 0, which was like, she knows measure theory, like, whoa. And I was like totally blown away. Anyway, so this girl, that was the only night she was in town from Wisconsin. She was there for a friend's birthday. I only saw her once in my life. It was that night. We exchanged emails, okay? We exchanged emails. And to this day, I still email her every 5-6 years. We'll email each other. She programs robots that build, weld cars together. So when a company like Toyota puts a plant together and they get all the machines in there, she goes in there and programs all the robots. Not just her, but her and her team, right? Very, very smart girl. Everyone always asks me, did you marry her? No, I didn't want another math person in my life at all, but. So the point of the story is what? Go get drunk every once a month. No. The point of the story is, when you're differentiating from here on out, we need to know with respect to what variable. It changes everything for us. What are we nudging? What is the thing we're going to change, the infinitesimal change in x? How does that impact everything here? All right? So let's go to our first real, why are we doing this? What's the point? I want us to look at x squared plus y squared is 1. Does anybody recognize that equation? Can anyone tell me what that is graphically, geometrically? That's a circle. That's the equation of a circle. If you go back to pre-cal, there's a formula in pre-cal. That is the generic equation of a circle that has a center at hk and a radius of r. So whatever this number is, right, take the square root of it, and that's the radius of the circle. And then this number and this number here, whatever they are, that's the center of the circle. Does that look kind of familiar from the past? Yeah? So this is that formula. If you replace h and k with 0, right, and you replace r with 1, then you get that equation, right? So that's the unit circle, isn't it? The unit circle, the circle of the radius 1. If I graph this, and I ask you to go to this x value, I'm just going to pick a random x value, and give me the slope of the tangent line at that x value, can you do it? What's the problem though? What's different from this and what we had before?
You got 2 y values?
You have 2 y values. This is not a function, right? Everything we've been studying up to this point, the graphs have been functions, meaning they pass the vertical line test, right? This circle does not pass the vertical line test. So if I say, hey, go out to x and tell me what the slope of the tangent line is there, you can't tell me yet because there's actually 2 places you could be talking about. You could be talking about this tangent line, right? Or you could have been talking about this x coordinate down here is the same, that tangent line, right? So which one are you talking about? I don't know, I can't tell, right? Does that make sense? So in this class up to this point, everything we've done, when you go back and look at everything we've done, even when we were like developing the whole idea of the limit, we said this was a function f, right? Here's x plus h. We're going to take this point, slide it over there, right? It required this being a function. It required the vertical line test to be passed. But in the real world, not everything is a function, right? Just think about like if I were to take a, I don't know, I'm just thinking of like a, I always think of like a bug, right? If I take a bug, just put them on the ground and it starts walking around, right? That bug's walking around the ground. It's not necessarily going to behave the way I want it to behave, right? But I still may want to talk about, you know, the change in direction, bug, a race car, a rocket through the air, whatever you want it to be. Things don't always have to behave where they pass a vertical line test, right? So our calculus shouldn't be limited to just functions, right? It should be able to handle things that aren't functions. And to do this, we actually have to be able to do this, right? We need the implicit differentiation in order to figure out how to differentiate and find tangent lines here, right? That's the whole point, right? So I would like now to ask this question. I would like us taking this, I would like us to find dy dx. Which for us, we realize that this has always meant f prime of x, right? It's the slope of the tangent line, yes? But see, we can't use this notation anymore because this is not a true function, right? It's not a true function. It's not solved for y. If I could solve this equation for y, then it could be a function of x. But right now it's not solved for y, right? What would happen if you tried to solve this for y? Take that equation, try and solve for y. You're going to have a square root. So hold on, let me do it. If I say solve that for y, you're going to have x squared plus y squared is 1. Okay, let's get the y squared by itself. Let's subtract x squared on both sides. And now let's get y by itself. So let's get rid of the square root. We have to take let's get rid of the squared. So we have to take the square root on both sides, right? And whenever you come in and take the square root on both sides, you have to do plus or minus. And now this is not a function. Because remember, a function means one input, one output. Here, because there's a plus and minus, it's possible for me to give you an input and you give me 2 outputs. And that fails to be a function. So you cannot tell me, you cannot say that you have a function that's plus or minus 1 minus square root of x. Not going to happen, all right? So you can't solve for y. But can we still find the slope of a tangent line? Can we do it, right? We know they're there, right? We know that there are 2 tangent lines. They have slopes. Can we find them? So what we do is this. We use implicit differentiation. I'm just going to put implicit diff. So how does implicit differentiation work? Well, like this. You take the original equation, and you're going to just take the derivative on both sides of the equation with respect to whatever was here. I'm asking for dy dx, right? So I'm going to take the derivative on both sides of this equation with respect to x. Does that seem reasonable to you, that we could do that? You have an equation, do the same thing to both sides, right? Differentiate both sides. All right, this, I think should be pretty clear now to us. What would the left side be? 2x times dx. Yeah, let's do it. Times dx. We'll go ahead and do the chain rule. That's the derivative of that one. Plus derivative of y squared.
2y dy dx.
2y dy dx. Done with that? Yeah? Equals? What's the derivative of a constant? 0. Now that will never change, okay? No matter what calculus class you're ever in, the derivative of a constant is always 0, okay? Because this is saying how much does this change by if I change x? Well, 1 never changes. 1 is just 1. So there's no change ever in a constant. So this is 0. Why did we do this? Why did I come in here with this equation? Why did I take this equation and do d dx? Why did I do that? Well, I did it because I was trying to find dy dx, right? That's what I was asked for, dy dx. And I know that since this has a y in it, and I'm differentiating with respect to x, somewhere in there I'm going to get dy dx, right? Right there. And that's what I'm solving for, right? That's what I want to know. So I'm going to now isolate this by itself on one side of the equation. Yes?
So we put dy with respect to y, or I'm sorry, yeah. dy with respect to y, what would happen?
So if we would have put d dy, right? Let's do that afterward. Okay?
Sounds good.
So this is a 1, right? That's a 1. So this is really, this says this, 2x plus 2y dy dx equals 0. And I want us to solve for this, right? Get this by itself, right? That's what I'm looking for, dy dx. So to solve just algebra, move the 2x to the other side. Divide both sides by 2y. And you get dy dx is what? Negative x over y? Yeah? Negative x over y. That's your derivative. Now let's try and wrap our heads around this. Up to this point in this class, every derivative that I've ever asked you to give me, your answer was a function of x, right? Like when we started class out. When I say, what's the derivative of x squared? Everyone was like, oh, 2x. Or if I say, what's the derivative of sine x? Everyone would be like, oh, that's cosine x, right? That was before today. And these are still correct. But the derivative of something that had x's in it, you got an answer with just x's in it. Look at our derivative here. It has x and y in it, doesn't it? Which means that in order for me to tell you the slope of the tangent line, not only do I have to give you the x coordinate, I have to also give you the y coordinate, and that's actually good. Because on this circle, I can distinguish between these 2 points now, right? This has one particular x coordinate and one particular y. If I plug the x and the y for this point into this, it'll give me that slope. But if I give you this x and y, which are different, right, than this one, I'm going to get a different answer. And that should correspond to this one. Make sense? Let's see if this formula makes sense to you. Like, let's see if it actually works in terms of what you would think would happen. This is going to go back and see if you remember the unit circle at all. What if I were to take the unit circle here, 45 degrees, pi over 4. What's that point? Root 2 over 2, root 2 over 2, right? My pre-calc class has a test on this today. Right, that's the point at 45 degrees, or at pi over 4. I'm going to put pi over 4 here. All right, what's the slope of the tangent line here? So if I were to get a tangent line, right, seems like the answer should be -1. Is it? Well, this is the x coordinate, right? This is the y coordinate. Plug it into this formula. Yep. If you plug it in this formula, you're going to get negative the x coordinate, root 2 over 2, over the y coordinate, which is root 2 over 2. And that's the same number, just opposite sign, so your answer is -1. Makes sense, right? I mean, it seems like the formula works, yes? How about up here? What's that point up there? That's the point 0, 1. Does it work in this formula? Plug in the x coordinate is what? 0 over 1. 0 over 1 is 0. The slope of that line is 0. Works, right? How about this one? What's the slope of the tangent line here? Careful. It's vertical, right? What's the slope of a vertical line? Infinite or undefined, right? We'd say it's undefined. Is that what happens? That's the point 1, 0, right? Plug that into this formula. 1 divided by 0, or negative 1 divided by 0 is undefined, right? It all matches. Does that make sense? That's pretty cool, right? So we have a master formula now that as long as you give me the point on the curve, I will give you the slope of the tangent line. And this will work for any curve, right? Any curve. So I'm going to refer to over here, I want to show you that the reason we call this implicit differentiation is because there's a difference between what are called explicit equations and implicit equations. An explicit equation is any equation where you can solve for one of the variables. So like here, I've solved for y, right? So I know what y is explicitly in terms of x. The next one, I've solved for y. That square root, I'm not sure why it's cut off there, but that's the square root of sine x. Again, it's solved for y, right? The last one there, it's solved for x. So if you give me y, I give you x, right? Those are explicit equations, and we can always differentiate those the way we were doing before we got here today. Implicit are equations that you cannot solve for x or y easily. Those are some examples. Now the first one we just did one of those, except I used 1 instead of 16, right? But I want to look at that next one. I'm going to graph it for you first. Because that first one right there, x squared plus y squared is 16, that's a circle, right? What's the radius of that circle? 4? 4, square root of 16, right? But what about this next one? What about x cubed? Nobody here knows what this looks like, okay? I don't even know what this looks like. But I bet you that there are some x's and some y's that I could plug in here to make this true. And all the x's and y's, all the ordered pairs that make that true, are solutions to that equation, are also going to be on the graph, or that's what makes up the graph. So I'm going to go to, oh shit, sorry about that. Okay, I'm going to go to Desmos and I'm going to type in x cubed plus cosine y, sorry, equals x plus y squared. Interesting. That is the graph of that relationship. There are points that you can find, x's and y's, that plug into this and make it true. And there's a lot that don't make it true, right? But those are all the points that make this true. It would make sense it would be useful if I could find the slope of the tangent line anywhere on that curve, right? Yes?
In regards to the implicit versus explicit,
Yeah.
is it typically going to be one that fails the vertical line test? Is it going to be implicit?
Is it typically? That's a great question. The question was, if it's implicit, will it fail the vertical line test every time? Implicit just means you can't isolate the variable easily. Let me think about that. I think it'll either fail the vertical or horizontal, one or the other. But I can't say that it will fail just the vertical. Like, oh, if it's implicit, it fails the vertical. It could be that it fails the horizontal but passes the vertical. All right, you ready to differentiate that? Oh, I never got to your question. What would happen if I did dy, right?
No worries.
Well, the thing is, I'll just state this. I would never want to do that because I was asked for dy dx, right? So since I'm asked for dy dx, I'm going to differentiate with respect to x. Had I done it, though, had I done it, if I did d dy of this, I can do it fast, so I don't mind doing it. If I did it with respect to y on both sides, right? Then I should expect to find what's going to pop out of this that's not going to go away. A dx dy is going to not go away, right? I'm going to have a dy dy, but that's going to turn into a 1. So the difference is this will be 2x dx dy. See that? That's chain rule on that. Plus, now this is 2y dy dy equals 0. That's the difference. See it?
Yes, sir. Thank you.
Yep. Okay, so for this one, I want us to find dy dx. The reason why we're doing dy dx is because dy dx is basically the slope the way we've thought about the slope this whole time in this class. It's the rise over run. So here we go. Implicit d dx on the left side equals d dx on the right side. Take a minute, see if you can get that on your own. Just crank out the derivative first. Then we'll solve it. We'll solve for dy dx together. How are y'all doing? Feel like you're getting it? I'm gonna put the answer up, or at least the derivative. You know what? I'll make this dx. I'll make it 1 on the next line.
In the end, do you pull out the common dy dx and separate it? Is that
Yeah.
how you end up doing the math at algebra?
Yeah, we're gonna do it. We're gonna do it. Yeah, this is a lot of times for student. This part becomes the easy part. The hard part becomes the solving for dy dx. Yes.
Do you have issues? My handwriting's pretty terrible, so I can't always tell the difference between my y's and my x's. I'm gonna write dy versus
Uh-huh.
dx.
Do I what? Do I have any?
I don't know. I mean, your handwriting's pretty good, but mine's pretty terrible, and I can't really tell the difference between my dx's and my dy's.
You know what I'm gonna say then? You got to fix your handwriting. Yeah. Yeah, do whatever you need to do. I mean, look, over time, like if I go back and look at what I was doing, like in the beginning of my math life, like my handwriting adapted quite a bit over time, like quite a bit. Like the fact that I print in capital all the time, that's just something that evolved. I didn't start like that, right? The fact that, I write my T's with a curve on the bottom instead of just like that, so I don't mix it up with a plus. My Z's are struck instead of a 2, right? All these little things just slowly adapted. So if you find yourself not able to like make out your own work, you change something, yeah. Another problem I had was with my U's. My U's and my V's used to look the same. And so I started doing U's with a little tail, and my V's, I like really exaggerate them, where my V almost looks like an are sometimes, but you know what I'm saying? Like, everyone, you just got to kind of find your own style. If you can't read it, then, you know, whoever's going to look at it's not going to read it either. And sometimes students are like, well, you know, I know how to do the math. Who cares that my handwriting sucks? I always look at it like, if you ever have to work with people, right? Like, let's say you're working in some engineering firm and y'all are working on a problem together and y'all are like, hey, look at what I've got. And you're like, what the fuck? You know, like, what is it? Well, I understand it. Well, you still have to be able to communicate that, right? Like, you want to be able to communicate your ideas across to somebody else. So, all right, that stuff comes with time. All right, so any questions on this? Plus between these, right? So I do them separately. Derivative of this, 3x squared, then derivative of what's here, dx dx. Plus, chain rule. Derivative of cosine of something is negative sine of that something. Then you got to take derivative of the y with respect to x, dy dx, right? Equals. Now over here, sum. Split it up into two. Derivative of x with respect to x is just dx dx. And then this one again, power rule with some chain, pop out the dy dx. We're good? That's going to turn into a 1. That's going to turn into a 1. So let me just clean it up. Right now we have 3x squared minus sine y times dy dx equals 1 minus 2y dy dx. Now, on my homework solution videos, you might see me not write dy dx. I might write y prime, just because I know that this is dy dx, but just so I don't have to write dy dx each time. Yes? What did I what? Yeah, I don't know why I wrote minus, actually. Thank you. Okay, so just be aware of that. In your homework, you might see this is a y prime, and that is a y prime. I don't care what you do. Just, you know, on yourself, I don't care if you use y primes or you use dy dx. I prefer dy dx, but those videos are already there. I'm not going to change them all right? All right, we keep going. I want dy dx, right? So I need to isolate it. So I need to get all my dy dx's together. I have a dy dx there, dy dx there. So here's the rule. Everything that has a dy dx, move it to one side of the equation. Everything that does not have a dy dx to the other side. So because that's a negative sine y dy dx, I'm going to move this entire term to this side, okay? And then this is a 1 that doesn't have a dy dx. I'm going to move that over here. So my next line will be 3x squared minus 1 equals the 2y dy dx plus the sine y times dy dx. That's just algebra, right? Moving terms from one side to the other, they just change signs. Do y'all know why I did that? I can factor out dy dx. These both have dy dx in them, right? So I can factor it out. So this becomes 3x squared minus 1 equals, pull the dy dx out like a factor, and you'll